Hello?
So the next talk is by Michela, Meister, along with Greg Valiant, a Data Prism, and you have some more in the title, I guess.
Yeah,
Right.
thanks. So hi, I'm Michela, and today I'm going to tell you about a Data Prism, which is joint work with Greg Valiant. So at a high level, our work is a data prism in that you feed in a large data set reflecting a bunch of different demographics, and we provide tools for extracting information about a specific demographic of interest, even if we might never know which data points belong to that demographic. So for example, let's imagine you're a large company like Amazon or Netflix. You collect a big data set of customer reviews of different products. So we have N products. We have M reviewers, where M is larger than N, and where each reviewer is going to rate at least R random products. And throughout this talk, we're going to be working with Boolean ratings, so a reviewer rates a product just by saying whether they think it's good or bad. Additionally, we're going to be thinking of N as fairly large, so N is greater than 1,000, and R is pretty small. R is only going to be, say, 3 or 4 products. Now let's suppose that long after you collect this data set, you'd like to learn the preferences of a specific demographic. So perhaps we care about graduate students. We'd like to learn which products graduate students think are good or bad. Unfortunately, when we collected the data set, we didn't have any demographic labels. So we don't know which reviewers actually are students and which reviewers aren't. But perhaps we do know that at least an alpha fraction of our reviewers are students. And additionally, we're going to assume that all of the students agree on which products they think are good or bad. So there's this underlying vector y that's going to describe the student preferences on the end products. Now, importantly, while we're going to assume that all of the students agree on which products are good or bad, we're making no assumptions about the rest of our reviewers. So in particular, the 1 minus alpha fraction of our reviewers who aren't students might be giving us random, arbitrary, or even adversarial labels, or adversarial ratings. So they might be colluding to try to mess up our understanding of the student demographics preferences. And so then our goal is going to be to approximately recover y. And as is, if alpha is less than a half, this can be impossible. So the ratings from the non-student reviewers might entirely swamp the ratings from the student reviewers. So in addition, we're going to be allowed to hire a small, constant number of student evaluators. And if we ever want to know the student rating of a specific product, we can hand this product over to one of our own students, and they can tell us the rating. So this is going to allow us to query k possibly noisy coordinates of y. And actually, just for sort of the rest of the talk, while all of our results sort of hold gracefully in the noisy case, I'm going to be mainly just talking about the noiseless case for simplicity. So then the main question is, how small can alpha, the fraction of our reviewers in the demographic of interest, be as a function of r, the number of items each person rates, and k, the number of queries we get to make to y? And also, so while this example is in the sort of market research setting, I think there are actually a lot of other interesting settings in, say, healthcare or medicine, which I'm happy to talk about later on today at the poster session. Okay. So the punchline is that if r is larger than 1 plus log 1 over alpha, we can recover an approximation to y with only a constant number of queries. And so constant here is going to be in terms of n, or is going to be with respect to n. So our constant is not going to depend on the number of products that we care about, but may depend on, say, the accuracy or confidence that we want, and alpha. So just to sort of emphasize why this is sort of surprising, this means that if each reviewer rates, say, only 5 products, then we're able to recover information about a demographic that might only make up a bit over a 16th of the population. Okay, so more formally, this means that for some accuracy epsilon and confidence delta, and r's we've described, we're going to have our constant k be dependent on epsilon, alpha, and delta, but not on n. And after querying these k random products, we're going to, with confidence 1 minus delta, be able to output an approximation to y. That's going to differ from the actual vector y in only epsilon n coordinates. And additionally, our algorithm is going to run in near linear time. So as stated, this is actually going to require n to the r reviews. So as stated, this is actually going to require reviews on basically all sets of R products. But if we assume that the non-students, the sort of adversaries in the problem, are not able to be adaptive to the k queries that we make, then we can do this with only a linear number of reviews. So basically, if we assume that they can't be adaptive, our results improve a lot. This is somewhat surprising in that if R is less than log 1 over alpha, it's pretty easy to see that we would actually need to query a linear number of products. And that's something I'm happy to talk about later. And so to put our work in some context, there's been a lot of great work on robust estimation and robust learning. The work that's sort of most similar to ours focuses on the setting in which a minority of the data is good. Sort of in contrast to previous work, which mainly focused on techniques from convex optimization and matrix completion, our approach, which sort of allows us to get this log dependence on the fraction of reviewers and the demographic of interest, is going to be entirely combinatorial, and actually comes from a pretty neat connection to constraint satisfaction problems, which I'm going to talk about now. Okay, so yeah, for the rest of the talk, we're going to assume that we're working in the noiseless setting and that we have at least n to the r reviewers. So in particular, for any set of R products, we're going to have a decent number of people who've reviewed that set of R products. So the basic observation is that if we look at any set of R items, there's going to be one assignment to these R items that is going to be forbidden by the reviews that we see. So just as an example, let's say that we have two items, y1 and y2, and alpha is 30%. Okay, well, there are 4 ways that a reviewer could evaluate 2 items, and we can't put 30% of the reviews on all 4 ways. So there's at least one assignment to these 2 items which has to be forbidden. So here, this is the true assignment. And this is all just because of how we're choosing R. Okay, and so this basically means that our problem reduces to this adversarial planted CSP problem, where instead of n products, we have n variables. And for every R tuple, there's going to be one assignment that's forbidden, but which is going to be consistent with this planted assignment y, which we're trying to recover. And so aside from being consistent with y, that forbidden assignment can be chosen entirely adversarially. And then we're going to be allowed to query a constant number of these variables. And our goal is to output an approximation to y. And so yeah, just as in the original setting, this approximation is going to only differ in epsilon n coordinates. And so then our theorem restated in this setting is that we have a near linear time algorithm for finding an approximation to y. And the main idea is that these constraints reduce the set of feasible solutions to at most a constant number of solution clusters, which we're then able to identify the planted assignment by querying only a constant number of variables. So I think there are a bunch of different interesting open questions and open problems. I'd be really excited to talk with you all more about these sort of open questions and also about more of the details of the work later on today. Thanks.
Time for a quick question. Please, Nati.
Mm-hmm. Okay, so just to make sure I'm understanding the question, the question is about we get to see all of the reviews, and then we get to choose which products our students query. Yeah, so that makes. So I guess here, I'd probably want to talk about it later. So
you guys want to talk about it later.
It's okay. The adversary, knowing that you could do that, could still make your life hard in how they assign their original reviewers to vote. But that should be easier than. Basically, that should be easier. I'm not sure if it improves the sample complexity. Is all I want to say. Yeah.
All right, let's thank the speaker again.
Thanks.